Hello everyone. It's my pleasure to represent our research team to share one of our latest research work. The title is PALM Prototype Aligned Label Manifold Learning for Multi-Label Classification with Partial Annotations. I'm the presenter. My name is Xin Zhang. I come from University of Southern Maine. We start from the background of our research. Compared with multi-class classification, multi-label classification that contains one than one class is more suitable in real-life scenarios. And in our research work, we focus on the multi-label classification problem. For the multi-label classification problem, essentially speaking, this is a supervised learning. However, for the supervised learning, it requires huge annotation cost. For example, let's have a look at the image. For the dataset, we have n images, and for each image, we have m labels. So we need to have m by n labels. That's a very huge number, especially for the large-scale datasets. If we are able to use partial label solutions, just like the second table, a part of label are missing. For this kind of setting, we can reduce the annotation cost. We can use p by m by n labels. P here is a percent of the retaining labels. And for the adversarial attacking target labels, for this kind of attack, they will remove labels. So our model is not robust enough for the current solution. The model is not robust enough, so the current model is not able to resist this kind of adversarial attacking. And we have two solutions to mitigate this problem. First one, we generate annotation automatically. For example, we use like AI tools, we grab from website to get labels. But the thing is, for this kind of label, it always comes with noise. So label with noise, it will reduce the performance of our model. And the second solution, we training with partial labels. Partial label means that only a subset of all the labels can be observed and the rest remains unknown. The second solution is very hot currently, and in our research work, we follow the second path to design the model. Related work and challenges. Related work, first one, binary relevance. The binary relevance is a very the method was proposed like 10 years ago. The basic idea is for different label, we use a separate binary classification network. For this kind of design, although we can get a multi-label classification result, but we discard the relations of the labels. So for the large-scale dataset, we always have a low-performance network. The second one is positive and unlabeled learning, so we use PU learning for short. For this kind of design, it can only handle the dataset with partial labels. If the partial label is also missing, we have no idea how to deal with this case, so it has some limitations. The next one, auxiliary network. We use an auxiliary network to generate labels for the missing part. But the problem is we have another cost. We bring extra burden for the computation because we introduce another network. This is a contribution of our PALM solution. In this paper, we propose a new framework called the PALM, which stands for the Prototype Aligned Label Manifold Learning, designed for multi-label classification when the annotations are incomplete. Our contribution mainly includes three aspects. The first one, when we embedded both image and labels into a shared semantic space. Instead of treating labels as independent binary classifier, we represent each label as a learnable prototype vector. These prototypes are further refined through attention-based message passing, which allow related label to exchange information. This is important because in real-world multi-label tasks, labels are often correlated. For example, person and bike may frequently appear together. By modeling these relations, our model can better learn under incomplete supervision. The second point, we introduced an optimal transport-based alignment mechanism to associate images with labels prototypes. Instead of making hard binary prediction for each label independently, we compute soft correspondence between images and labels. This allows the model to assign probability mass to multiple possible labels while respecting global constraints. As a result, the method becomes more robust when some labels are missing. The last one, we corroborate two additional strategies to improve learning with partial labels. First, we apply manifold regularization, which encourage visually similar image to have similar label predictions. This helps propagate supervision across the feature space. The second point, we design a curriculum pseudo-labeling strategy guided by uncertainty estimation. The model first learns from reliable predictions and gradually incorporates more pseudo-labels, which help reduce confirmation bias during training. The next one, I want to introduce our PALM model structure. This page shows the overall architecture of our proposed PALM. Start from the left side. The model first takes an input image and passes it through a visual encoder. The visual encoder here is a convolutional backbone. We use this backbone to extract high-level visual features. At the same time, we maintain a label prototype module. The label prototype module is over there. Each label category is represented as a learnable embedding vector. These prototypes are initialized using a global word embedding, which provide a semantic prior knowledge. And after that, we refine them through self-attention layers, which allow different label prototype to interact and compute and capture label relations. The next, we compute the association between image features and the label prototypes using an optimal transport alignment module. Instead of independent classifier, optimal transport builds a transport plan that assigns probability mass from the image to multiple label prototypes based on their similarity. This produces soft label prediction, which are more robust when labels are missing. As a comparison, for the traditional solution, they prefer to use a hard label prediction, so it will make the prediction is not so smooth, so it will reduce the robustness of the solution. So we select a soft label prediction. After that, we apply manifold regularization. We construct an graph in the visual feature space so that images are visually similar will encourage each other to have consistent label predictions. This helps propagate supervision even if some images have incomplete annotations. Finally, we incorporate a curriculum pseudo-label module. Using Monte Carlo dropout, we estimate the uncertainty of predictions. Predictions with low uncertainty are gradually selected as pseudo-labels and used as additional supervision during training. All these components contribute to the final training objective, which combines the classification laws, transport alignment laws, manifold consistency laws, and pseudo-label laws. Due to the time limitation, I do not elaborate on our loss function design. If you are interested in the loss function design, please refer to our paper. The dataset, we select 3 datasets to conduct experiments. The COCO not wide, and particle walk. The next, I want to show our experimental results. The first one, we conduct experimental result. We conduct experiments on the FAL setting. FAL setting is short for the Foley annotation label, which means in this setting we have all the label observed. And you can notice the last row is our performance. We beat the baseline models. We are the best one in the FAL setting. It demonstrates in the Foley annotation labels setting we have the best performance. The next one is the PAL setting. The PAL setting is short for the partial observed labels. For the partial observed label, our solution is also the last row, and we bought the performance is obvious. We beat the other baselines. We are the best one. For the PPL setting, PPL is short for the partial positive label. For this kind of setting, only a part of positive label is observed, and the rest we discard. For this kind of setting, we still beat the other baseline models. So from this group of experiments, it demonstrates we get the best performance in all the label settings, no matter Foley label, no matter partial label, no matter partial positive label, all the settings, we are the best one. The last one is a single positive setting. The single positive setting is a special case for the PPL. Single positive setting, so from the name it's easy to understand. For each image, we have only one single positive label, and the rest we discard, and we still the best performance. Okay, so that's all the content of my presentation. If you have any question, please contact me at my email address. Thank you for your time.